All right, for this video, we are going to be going through some examples of each of our decay or emission reaction types and predicting daughter nuclides. Our first one will be alpha decay. So remember, we can use the word decay or emission interchangeably. They mean the same thing. And so these are again going to primarily happen to our heavier radioisotopes. In our example, we are working with uranium-238. Undergoing alpha decay. So remember, alpha is on the product side then. And remember when we discussed balancing before, we're balancing the atomic number and mass number here. So I have a total of 92 protons on the reactant side. That means I have to have a total of 92 on the product side. I already have 2 from the alpha particle, and so that leaves 90 for my daughter nuclide. That is a 90, by the way. Let me fix that. Okay. We do the same thing with our mass number. So we have a total of 238 on the reactant side. We already have 4 from our alpha particle. The remainder has to be in our daughter nuclide. So of course we're subtracting here. 238 minus 4 means we have 234 left over in our daughter nuclide. And for this, I forgot to mention at the beginning, very, very, very helpful to have your periodic table handy, unless you have it memorized, which would be weird. So anyway, we find number 90, and that is it on the very, very bottom row in our actinides. And the fun part with this chapter is naming elements we never get to work with. So I'm going to give you a second. Guess the name of the element TH. You've probably heard of it before. This one's not too off the wall. Thorium, named after the Norse god. And so we have created thorium-234 in this reaction. All right, going a little bit faster for our next examples, we're going to follow the same process here. With each one, I've given a description of what's happening in this process. Again, you don't need to memorize this, but understanding what happens in here will make it easier rather than trying to just go through the numbers. So in a beta decay process, we are converting a neutron to a proton and an electron. Remember that electron is our beta particle. So when it gets converted to an electron, that means that we're emitting the beta particle. Notice and remember that the beta particle has the atomic number of -1. So for our math here, if I'm starting with an atomic number of 89, in order for the math to check out, it means that our protons, our atomic number, is actually going to increase, sorry about all of that, is actually going to increase by 1. And so in this one, we actually produce element number 90 again. So we're producing thorium again. However, we're going to have a different mass number. Notice since a neutron is being converted to a proton, our mass number doesn't actually change here. So we have created thorium-228 in this decay process. Our next example is gamma decay or emission. Remember, gamma particles have no numerical values, right? There's no mass, no protons, no neutrons associated with them. So we often write gamma decay reactions in conjunction with other types. So it might happen with a beta particle, as is shown here, or it could be combined with an alpha particle. If I just wrote gamma decay by itself, obviously the numbers wouldn't change at all. At this level, again, we don't expect you to predict decay types, but if we have a really, really unstable isotope, 2 ways that we denote it. One, we might put in a star or an asterisk after the mass number. A second way we could denote it is to use the letter M after our mass number, and that letter M denotes that it's metastable or very unstable. So if you see either of those notations, this substance is going to undergo gamma decay. For this one, because it's happening with beta decay, we're predicting products the same way. Again, our atomic number has to increase by 1 in order to make the math check out, right? A 67 minus the 1 gives us a 66. dy, by the way, fun new element for you that you've probably not worked with. or talked about. Dysprosium. You're welcome. And of course, again, in here, our mass number does not change. And so for this one, when we check our periodic table, I don't have it memorized. I have to check still too. We see element HO, and that is holmium. For our next example, we're talking about positron decay. So positron decay, remember positron is the antimatter particle of the electron, so it's a positively charged electron. So here's an example showing what happens basically when we have an electron react with a positron, we generate a gamma particle. So in this example, we have positron decay. So the positron particle is on the product side. Again, we have a +1 here. That means our atomic number must decrease by 1 in order to make the math check out, right? The 18 plus 1 gives us the 19. Again, our mass number does not change. Very nice in a lot of these that that's the case. And when we check our periodic table, this is argon. Electron capture is the one different type of natural decay process. So this one is exactly like it sounds. First of all, there is an electron, so a beta particle. Capture means that it's actually going to, that the isotope is actually going to capture an inner shell electron. So if you remember your electron configurations from first semester, we have that 1s shell that's right outside the nucleus. And in that 1s shell, we have an inner electron. So that inner electron can be captured by the isotope. And notice we get the same results as we would from positron decay. So our atomic number decreases by 1. When that happens, we end up forming titanium with an atomic number of 22, and we still have a mass number of 49. To make sure that all of this makes sense, here's a great practice slide for you. So the answers are left here, but on the left side, I tell you the decay process, the original isotope, and I want you to predict the daughter nuclide that is produced from each one.